All right, it's Cal 1 Applications of Differentiation. We're working optimization problems. And in this particular problem here, let's read it out. We're going to find the length and the width of a rectangle whose perimeter is 200 meters and has a maximum area. So let's go ahead and translate that into some equations. All right, so we're looking at a rectangle, and I guess I'll just draw a picture right here so maybe we all know what a rectangle is, even though I'm going to do my best to try to draw a rectangle. Okay, there's our rectangle. Let's say that's our width and that's our length. So we're trying to maximize, we want to find the dimensions that gives us the maximum area, but we've got a constraint here, and that's going to be the perimeter. So remember that the perimeter is going to have to be 200 meters. So let's just go ahead and first write our two unknowns, the length and the width, and 200. So this is just given information here that we're going to need. Now let's go ahead and set up an equation here. Actually, I'm going to write the primary equation first. So we're trying to maximize our area, and I'm going to write just max here and the area, right? So if you remember from third grade, the area of a rectangle is length times width. And let's go ahead and write the equation out for the perimeter. So remember, the perimeter is this distance all the way around. If we were to measure this all the way around, okay, and we're going to end up having 200 is the perimeter, and that's equal to 2W plus 2L. Okay, so we have our primary equation, we have our secondary equation. Now what we're going to want to do, remember, is get this thing all in terms of one variable, either L or W. And I think what I'll do here is just solve for L in this equation here, or solve for W, solve for L. Anyway, let's just do this. I think the easiest way to do this is multiply the whole thing by a half. Okay, multiply 100 by a half, and a half, so we can get rid of these coefficients here, these twos. So if I multiply this by a half, we'd end up with 100 W plus L. Okay, so that makes things a whole lot more, a lot simpler here. And I'm going to go ahead and actually I'm going to rewrite it like this, so hopefully you can follow me here. Just take the W over to the left, and so, but then I'm rewriting it, flipping it around. Surely you can follow that, right? We got things in terms of W, and now I'm going to go ahead and take this and plug it in directly up here. So rewriting, we're going to have A is equal to 100 minus W, let's put some parentheses around that, times W. So we got our formula up here, and it's in terms of W. Now I'm going to go ahead and distribute that W across, because remember what we got to do next, and that's take the derivative. So 100 times W minus W squared. But you know what, I think before we even do all this stuff, I think what I'm going to do is actually graph this. And remember, we're trying to find a maximum here, and I'm going to graph this, and let's just try to get an approximation first. Alright, so let me bring this graph up, and we need to zoom out on our y-axis, but we're just going to leave it like this. Okay, so as you can see here, let's actually scroll down. Okay, so this is the graph of the perimeter, I'm sorry, the area with, I think we got it with respect to W here. As you can see here, we're at 50 and then 2500. So this X value is what we're looking at. So we should be coming up with 50 in our problem. Alright, so what we're going to want to do is take the derivative of this thing. So I'm going to write A prime is equal to 100, right? The derivative of 100 times W